Okay, so Ravi, maybe you can switch your slide on. So I'm Vincent Morel from Mines Paris in France. So I'm very delighted to present you today Ravisankar Naraparaju from DLR. So he will start the discussion about key challenges and implication of CMAS on TBCs. So afterward, Thomas Brunet from Onera will give also a talk, and then we take some time at the end of the meeting to have a dynamic discussion with all of you. So don't hesitate during the talks to ask some question using the chat. And by this way, I will try to do my best to have this exchange. So the meeting, the webinar will end at 3 p.m. So Ravi, the stage is yours. You can start when you want.
Yeah. Thank you, Vincent, for asking me to give this talk, and I'm really happy to give the talk about the knowledge that we have acquired during last 15 years in DLR. So I try to show some aspects what we have observed, and I would like to really give some kind of information so that work can be done extensively all around the globe. So my topics, I think as you have seen here, there are so many people here involved. It's not only my work. So several PhD students of mine, Cynthia Garcia, Christoph Mikula, Lars Steinberg, Juan Gomez, and co-workers, Peter Meshnich and Uwe Schulz. And then we have collaborated with several people from the USA also, like from the University of Central Florida and now Embry-Riddle University. I think I have prepared so many slides, but I'll just run over a few things and depends upon the time. Now, I just like to motivate the CMAS problem. I hope many of you have already, experience with some of the CMAS problems, but just to give a glimpse, I will just show my pointer. I think I hope you see my pointer here. So generally, high pressure turbine blades are based on made of nickel-based superalloys, and they have some kind of bond code. Depends upon system. Some people have platinum aluminides, gamma prime, M Crowley, and then you use EBPVD technique, electron beam physical vapor deposition technique, to deposit low thermal conductive ceramic coatings, which are in this case 7YF is the state of the art, 7 weight percent ATR stabilized zirconia. And then when you have environmental effects such as dust, sand, volcanic ashes in the atmosphere, and then if you happen to fly through those clouds, or if your engine is getting a lot of dust from those environments, then this beautiful freshly coated TBC blades will look like this at some of the areas. The CMAS, or why we call CMAS, is it's made of calcium oxide, magnesium oxide, aluminum oxide, and silicon oxide, major constituents, and that's the reason that if you see, after the operation, your TBC will be, contaminated with molten CMAS and everywhere, and some parts maybe that would be, CMAS is molten and infiltrating those open porosity of EBPVD columns, and then stiffness increases, and then it will lead to spallation. So as you could really see, there were a lot of studies all over the world to understand, but mainly they understood that this is a typical capillarity issue. So if you have a molten CMAS, and then you have these columnar gaps, which are schematically shown here, and then this CMAS, once this melts due to the capillarity, it will just go down. But in real atmosphere, you have a thermal gradient because the hot gases are creating a higher temperature here, and due to the thermal barrier coating and this cooling, you will have a very low temperature here. So you have a thermal gradient established across the TBC. So after some, like 50-60 microns depth, the temperatures goes to like maybe 1150, 1160, or 1200, depending upon the CMAS composition. It will crystallize again, and then your coating will be, half infiltrated, and then after, during some thermal cycling, the crack happens here, and then the CMAS infiltrated area chips off, and that's how you see the parts. So as typical examples, I'm also going to show you some of the examples of the hardware. This is a vein where you could see, in principle, it should be completely coated with the CMAS, so TBC, and then as you can really see, the molten particles are mainly CMAS particles, but this part, the TBC, is basically spalled. And then I just want to show you the profile that many people think that CMAS infiltration will be uniform, but it depends upon the hotspots. And at this particular spot, as you can really see, the CMAS, we have done the EDS mapping, the calcium, silicon, magnesium, aluminum. You can track down that most of this coating has been infiltrated. If you just move to a few millimeters, then you find some areas where only upper part, maybe 25 to 30 microns of CMAS, 30 microns of TBC is infiltrated with CMAS. So basically different infiltration depth at different positions on the same vein, and this is what reality. So in engine you see all sorts of infiltration. So whatever we do in laboratory isothermal experiments does not really resemble the engine conditions. So engine conditions are completely different. So based on all our experience on a lot of experiments, we figured out that TBC damage is basically controlled by the composition of TBC and composition of CMAS or volcanic ash. And microstructure may have huge influence, because in the engine parts, in some parts are coated with APS technique, and some parts are coated with EBPBD, and then also these are all ceramic coatings with respect to time. They sinter a lot, and then depends upon temperature gradient, which defines the viscosity of CMAS, and time. So basically it's a chemical reaction, and infiltration speed is controlled by the time. But most of the things are basically, these two parts are controlled by flight profile or engine type, so it depends upon that. And most important point I want to really tell to the community that there is no standard single CMAS. And in the initial, let's say 20 years ago, when UCSB, University of Santa Barbara, they have used only so what we have UCSB, so they have started with the calcium, magnesium, aluminum, silicon, but over the time we learned that each engine has different deposits, and then we come up with like iron containing and titanium containing CMAS. And also if you see in the volcanic ashes is rich with silica and very low with calcium, so we could really grade them into low basicity index and high basicity index. So high basicity index is like the high calcium and low basicity index. Basically, we have done a lot of experiments between 1250 degrees to 1400 degrees centigrade. We varied deposition from 5 milligrams to 20 milligrams centigrade. So this is more like the experimental matrix that we have used to understand the CMAS degradation mechanisms. Now, we have studied several systems, but I'm going to concentrate on very few systems here. 7-YSZ, and then we worked on yttria-rich zirconates, and we worked on gadolinium zirconate, EBPBD, and most of the times we worked on microstructural optimizations, and then we have tried to do some simulation and develop non-destructive techniques to understand whether it is easy to get some data for modeling. We need a lot of data, and then non-destructive techniques would be useful to give us some data. Now, also the most important thing, the CMAS can also work in this corrosion erosion regime, and then we would like to understand the erosion properties. I'm going to show you 1 or 2 results on that aspect as well. Now, and like 15 years ago, there have been several efforts in the literature to reduce the thermal conductivity of TBCs. So one of the approach was to vary the microstructures of EBPBD, so to create more longer feathers and intercolumnar gaps. You can play with microporosity, macroporosity. That has been done in DLR, and they have seen that there is a huge improvement in the thermal conductivity. And that's where our thought process came, okay, whether we could really create 2 different microstructures or a lot of microstructures and see whether microstructure has a huge effect on the CMAS infiltration. Now, in this case, we created 2, with the EBPBD, we created 2 microstructures, namely normal and feathery microstructures. The details are here. Basically, if you see the surface analysis, so this is what normal microstructures, long and the brighter pyramid structures, and then feathery microstructures, we have created a lot of porosity. And we have done some infiltration tests at 1225 degrees centigrade where our CMAS composition is not completely molten. That means it gives us extra time to really resolve the infiltration kinetics. As you can see, we have gone up to 30 hours of infiltration, and at 1225 degrees, the normal microstructure, the standard microstructure, it has already infiltrated after 20 hours. So we have like 400 microns thick coating. But feathery microstructures, we have observed that this could really reduce the infiltration kinetics a lot. Then we went to a little bit higher temperatures, 1250, where it is readily molten. It's a high, very, very less viscous. The infiltration goes like top like that. Under no thermal gradient, it just takes, 3 to 4 minutes for normal microstructure and 8 minutes to feathery microstructure. That means we could see the effect of microstructure even at 1250 degrees in isothermal. So the idea here was simple. So if you remember two columns, so for example, this is one column and this is another column, and we have feathers, and then this is the normal microstructure where you have a columnar gap. That means the brighter columnar gap and shorter feathers. These are the shorter feathers. And if you could create a more feathery microstructure, that means if you could create longer feather arms and then reduce the columnar gap, then our idea is to reduce the infiltration depth, because I told you the lifetime depends a lot on the infiltration depth, which I'm going to show you also further in coming slides. Now, idea is if we could really split the viscosity, if we can split the capillary forces by creating longer channels, not in the principal direction, then it might work. And that is what we have tried in the microstructure, and we have seen that, and then we adopted this microstructure for another TBC. So I will show you in a few minutes. Now, we have done some modeling as well as so the FEM simulations, but here there are a lot of models. First of all, if you take this one, as in this is an open pipe. Let us say you have one feather column and another column, and you have a feather gap, and that what we call is a open pipe model. But in principle, this is not open pipe because you have a concentric pipe. So that means this is the gap around the column, and then you have a concentric pipe in between. So the infiltration kinetics will be completely changed. And then the most of the times we figured out this porosity fraction and geometric factor really defines the infiltration kinetics. So all our efforts were trying to change this porosity fraction and geometric factor. And then this is the experimental work, but we can't really create such kind of variations in the microstructures, which will really cost a lot of time and money. So we went to do some modeling on that aspect. So basically, if you take the feather arms, that's what I was talking about. So these are the feather arms. So this is the columnar gap, and most importantly, if you are really thinking about experiments, then if you could really see a difference between columnar gap area to total feather arm area, you can control the CMAS infiltration as well as CMAS kinetics. And that is the most important thing. If anybody is really interested to change the porosity in EBPVD microstructures, they need to concentrate on this, change the columnar gap area and also total feather arm area. Now, we took this as a microstructure unit cell. So simple one unit cell, we went for finite element methods. And then we have taken so many variables, like what you can really change. This is easy in simulations rather than real EBPVD process. So you can go with pyramidal angles, you can change the feather inclinations, feather arm thickness, void between feathers, so whatnot. So whatever possibilities that a microstructural feature can be changed. So we adapted to that, and then we tried to come up with a geometrical modeling of a column, and then we could create this one columnar gap with this feather arm lengths, and then we went to Python script to create so many different varieties of columns, column length, feather arms, feather arm angles, pyramidal angles, and so on. So it's also published data, so I'm not going to explain more, but the basic idea is to simulate the better microstructure for CMAS infiltration resistance, we need to come up with a model, and that model resembling the real microstructures. And that's what our first try was. And then I think even if you see this, what we defined as a throat area, so you have some places larger throat area and smaller throat areas. So without changing any feather angles, feather lengths, and so on, if you change the longer and smaller throat areas, you can also see the difference in the infiltration time. But the most importantly, this is, like I said, in this modeling, we have not applied temperature dependent viscosity. We have not applied thermal gradient in the system. We have applied, even we could not apply the capillarity force in this system. So we have applied some pressure difference from top to bottom and then created that kind of microstructures and see what happens. For example, the difference between A to B is shorter feather arms and longer feather arms. And C and D is feather angles are changed from 40 degrees to 60 degrees. And then if you see the E and F, you have 40 degrees with the smaller feather lengths and 60 degrees for smaller feather lengths. You can see clearly the difference in between the infiltration kinetics. But like I said, this is the first model we have started with. Then we went up with the finite volume methods and so on, which I'm not going to explain it here. But this kind of modeling would really help us to understand the infiltration kinetics, provided we can give time dependent, temperature dependent viscosities, and also thermal gradient. And if you can apply capillary force, then you can simulate the infiltration kinetics in normal EBPVD microstructure. Now, but real microstructures are different. So we went to nano-CT and to just get the porosity in individual columns. And then we could really create and get the porosity information. And then with this porosity information, we can directly go to the CFD simulations. And then we have done some work, which I'm not going to show. But if you are interested in that, you can use some methodologies kind like CT scans, nano CT scans to really get the microstructure. And then you can directly transfer this microstructure into your FEM simulations. Now, another non-destructive technique method, like I said, CMAS, which is thermomechanical, thermochemical, and infiltration 3 problem. So, but a lot of times we lack of data. What is the stress situation inside? What is the strain situation inside? And what is the toughness of your coating with the chemical reaction? Are you losing some of the phase destabilization? Certain kind of data, you can access it easily using Raman microscopy. So we have worked with confocal Raman microscopy and compared to conventional surface measurements. So we have used some CMAS measurements. We infiltrated CMAS for 5 hours. And then you can see as the CMAS is infiltrating, it's reacting with 7-YSR and taking some of the atria. So tetragonal phase is changing into monoclinic, and we were trying to get the monoclinic phase volume fractions, as you can see with respect to depth on the surface where you have a lot of CMAS which has reacted with the 7-YZ columns. You have around 40 to 50% monoclinic phase volume fractions, and as you go deeper down to the TBC thickness, then the reactions are like it's not so much. So you can see a change in the monoclinic volume fraction. At the same time, if you see clearly the column edges, and these are 2 columns, and this is the columnar gap where you have a lot of CMAS, and this CMAS is reacting with your 7-YZ, and your tetragonal phase is losing and so the TBC is changing into monoclinic phase, which is where you are losing your toughness. This is very important, where I am going to show you one of the results afterwards. So, and I wanted to show that with the information with the monoclinic phase volume fractions, at the same time using Raman data, you can also get the information from residual stresses. So this is a simple example. If you have standard 7-YZ, which is sintered for 10 hours, so it's a slightly compression, and then we have some CMAS infiltration for 1 hour at 1250 degrees, and then we found out these monoclinic regions are turned towards to tension, and even if you are going to 10 hours at 1250 degrees, then you see more areas which are converted into monoclinic, And then, so this is how you can really get also the data, how much is your stress situation of an infiltrated or reacted TBC. So that data we can also put into modeling afterwards. Now, simple thermomechanical models are used to really know to get this stress situation and what happens to the lifetimes. I'm not going to explain much, but simple experiments we have done. We have done some furnace cycle tests. So we infiltrated and we did the thermal cycling, and we have used the thermal gradient test rigs where we use a flame based on methane and oxygen. We put the sample here. For example, we can we insert some thermocouple inside the sample so we can measure the bond core temperature, and the surface temperatures are measured by pyrometry. And if you see, there is a sample of a TBC coated sample, and we put CMAS on top, and then we can basically establish the thermal gradient. That means we infiltrate the samples with CMAS under the thermal gradient. And then, like, if you want to really, do thermal cycling under thermal gradient for so many cycles, it's very expensive. So we try to come up with a method where we can really use a combinatorial approach between the typical furnace cycle test and a thermal gradient infiltration test. So where we have come with matrix, I'm just going to explain something. So we don't have any CMAS. We simply put for furnace cycle test 1100 degrees centigrade, and second experiment is we infiltrated under thermal gradient for 1 hour at 1250 degrees, and then we put to furnace cycle test and 1300 degrees centigrade. So it means we increased the infiltration depth, and we went to furnace cycle test. And the third one is purely furnace cycle test. Now it's a thermal cycling under thermal gradient. So now these are the results I wanted to show. A simple system, it's an Inconel 100 system, and then without any CMAS, we have a lifetime of, let's say, 850 to 900 hot hours. And if you infiltrate that CMAS, let's say 50% infiltration, and if you do the furnace cycle test, the lifetime goes down to 33%. And if you infiltrate to fully infiltrate, and that means your TBC is fully infiltrated, your lifetime goes to like 90%. And these are the tests in furnace cycle test. In comparison, if you go to purely thermal cycling under thermal gradient without any CMAS, let's say we stopped, there was no spallation, we stopped after 83 hours. That means around 1000 cycles, 5 minutes heating, 3 minutes cooling. And then if we put like half infiltration of CMAS, then the lifetime was reduced to like 48 hours. And then if we increase the infiltration depth, let's say, if it is fully infiltrated, the lifetimes went to 10 hours. So as we can clearly see, we don't need to run to understand the lifetime degradation purely on thermal gradient test. Rather than we can use combinatorial, like we can compare, we can just infiltrate in the TBCs, and then we go to furnace cycle test. Even then the lifetime changes because of CMAS infiltration can be easily figured out. Now, just showing where the spallation happened. So this is the furnace cycle test. Exactly, the crack starts, and then spallation happens in between, infiltrated and non-infiltrated area. In the thermal gradient, also you see the crack exactly happens in between the boundary between infiltrated and non-infiltrated. And then you can clearly see the crack propagates through the TBC like this. And just give another, so we recently worked with Vincent to figure out what happens to the fracture toughness and what happens to the failure mechanisms when you have a CMAS infiltrated sample. We have used laser shock experiments. For example, this is a typical laser flash we used to get a crack at the TGO TBC interface and a normal 30 FCT cycles at 1100 degrees. Just give me 1 second, please. Sorry. And so as you can really see, these laser shocks have exactly, given the debonding at the TGO and TBC interface. But if you have the CMAS infiltrated sample under thermal gradient, we have different cracks. So we applied the laser shock, and then the laser shock normally created certain kind of different variations of cracks. And then if we closely observe, and this B-type cracks and A cracks, so B-type cracks, they were not exactly at the interface rather than at a distance, and A-type crack where there was no infiltration, as you can really see here, that the A-type cracks are at the interface, like here in the case. So wherever there was no CMAS infiltration, the cracks were forming at the interface. Wherever there was infiltration, and depending upon the infiltration depth, the cracks are moving up and down. So that gives an idea that CMAS infiltration obviously controls the local toughness, but this LASART, the laser shocks method, can detect the weakest point of the CMAS infiltrated TBC. And in this method, we would like to really get the data for the fracture toughness and to put into the model. Now, I'm not going to talk about the models. It's a simple model. There is nothing so strange. We have taken the values of toughness and increase in the toughness or decrease in the toughness because of CMAS infiltration. But the real thing, what I wanted to show, that doing some small finite element method modeling, what we can see is the changes in the radial stresses at the infiltrated CMAS area to non-infiltrated CMAS area. So for example, here you can see the shear stresses where there was CMAS and no CMAS area, they are the highest point. That's where exactly you see the spallation. And now considering the infiltration model, infiltration kinetics model, and the mechanical model, and putting all the data, we could really try to get the TBC lifetime data. Now I think I have 5 minutes. Now, so we worked with also, we stopped with the 7YZ. Obviously, we are working on that as well. But yttria-rich zirconates can give pretty good lifetimes, pretty good CMAS infiltration behavior, and so the thing is, we have a EBPVD system which has where we can have basically 2 ingot materials. So for example, we can use 2 ingots. And then we can develop in one single run any kind of any kind of chemistry. So that's where we have understood this yttria-rich systems, which are basically cubic yttria, and then we have in one single run, basically like this. If we put samples here, and then we could really get a gradient in the yttrium oxide concentrations. And we have created 45 to 67 yttria rich zirconates, and then we put some Iceland volcanic ash on top. And then as you could clearly see, with 45%, there was no big reaction happened, and the CMAS was infiltrating. As you go up with yttrium oxide, so by 67 yttrium oxide concentration, we could see the reaction was happening. Some garnets are building, and also apatites are building. So in the one experiment, we figured out, okay, 67 yttria stabilized zirconia are much better to CMAS resistance. So then I'm going to skip. So we studied a lot on 65YSZ, and then like I said, there is no single CMAS that can really give us the mechanisms. So we had tested with a lot of volcanic ashes and CMAS compositions, and see what happens to one particular composition, how the reaction products look like. So in volcanic ash compositions, the reaction products give more dislocates. And CMAS with the higher calcium content, the reactions give us garnets and apatites and so on. So this is one typical example. If we are thinking about new chemistries, and then you have to really use various CMAS compositions starting from low calcium content to high calcium content to see how the reaction mechanisms and how to understand your protection behavior of your TBC. Now come to the gadolinium zirconate. This is also very important because gadolinium zirconate has been used as CMAS resistant coating, but we have studied the variations of microstructure of gadolinium zirconate in EBPVD. So we varied so many different parameters, and then we have created several microstructures. I'm just showing 4 different microstructures, so we could see a big difference in the porosity. But the same CMAS, if you put on all different microstructures, same gadolinium zirconate, but you can see a clear difference in the infiltration depth. That means even for novel TBCs, which are good against CMAS, there is a huge scope for microstructural optimization. Now, I'm going to skip the erosion properties because I don't have time right now. Just the last point is very important. Yeah. So then we come up with a new composition of gadolinium yttrium zirconate. So similar method in EBPBD, we have used the gadolinium zirconate ingot and yttrium oxide ingot in single run. We could create a huge variation of compositions. So, and also if you vary the composition from yttria high to yttria low, gadolinium oxide low to, so you can see clearly a huge difference in the microstructure. The phase diagram shows most of the compositions are in cubic fluoride area, and then this one we could really see if you're in 65Y, so it's a simple CMAS infiltration test for 10 minutes, and then you go with this composition and then comparing to gadolinium zirconate, this composition is the least infiltrated, so it's really reacting faster and creating that kind of CMAS resistant pair. And then we stick to this composition, and then we have tested up to 1300 degrees up to 5 hours and compared with the gadolinium zirconate and pure yttrium 65 yttrium zirconate, and still what we see is this composition yttria gadolinium zirconate is possibly the best CMAS resistant coating in this in compositions. So I would like to really conclude my talk. So I don't want to talk too many things, but I think CMAS problem still exists and persists. So now we are here to solve it, and then thank you very much for your attention.